are, there we go, awesome. So we are recording now, and I'll make sure I'll upload that to YouTube as soon as I am able. And it goes without saying, which is funny because I'm saying it, since I'm recording their lectures now, I'm not going to upload the lecture notes just because now you have a video. So, and that means my lecture notes can be really big and messy, and I don't have to worry about making them presentable, which is easier on me. So yeah, so we're starting our little problem power marathon today. So we're gonna do a bunch of problems today, all ranging over the material from 9.1 to 9.6. We'll do the same tomorrow, and I'll upload an additional problem video or lecture over the weekend because I figured most of you aren't going to watch a video during the week. You're more likely to do it over the weekend. So I'll post that after class on Friday, which is tomorrow. But yeah, we're going to get down to business, start doing some problems.
I guess a suggestion. I guess that's what that is. Is it possible for us to do some problems and then as we're doing a problem, or like after a certain point in time, like you do it, and then essentially we get to check our work and then you explain where we might go.
Can I answer that a little bit, Murphy?
Yeah, like
Yeah, go ahead, Nick.
Every once in a while. And that like we could totally do that like today if we're doing like just problems.
If you I mean, I can't say anything about the other lectures, but if you all agree to turn Mondays a little bit into that, like half and half, and Murphy's okay with it, then I'm fine doing that too. But regarding the other stuff, Murphy, take over him.
Oh, I have a question. You know when we're gonna get those quizzes back?
You'll have quiz 3 tomorrow.
Isn't, oh, okay.
Yes, I was going to say, Jackson, what you're describing sounds absolutely wonderful. And I wish I had infinite time to do that because that sounds awesome. But I will say that the venue for that is tutoring, which I highly encourage everyone to pursue. There's a whole ecosystem of learning in college, and the lecturer, myself in this case, can only do so much, and that's just how it works. Believe me, I'm doing more than the average bear in terms of trying to give you guys some real to try to model problem solving and give you guys some more hands-on experience. And maybe tomorrow we can, I want it to be more interactive for sure. It's a little hard to do over Zoom. Right. But I will say, Nick has got office hours. There are other tutors at VW. There are tutors all over the place. And that's really where you can get that sort of intimate back and forth that I think everyone should get. And it's just a part of how the ecosystem works in college. I've been a tutor for a decade now. I tutor still to this day. And it's a different dynamic. And I think it's a really important one for people that are learning stuff for the first time or struggling or whatever. Just sometimes you just need someone else's perspective. You need a little bit more intimacy from your learning experience. So I feel you, Jackson. And we'll see if we can make it a little bit more interactive tomorrow. But I can't.
Fine. Again, I was just throwing something on the wall.
No, it absolutely, it would be wonderful. But if we did that in 50 minutes, we might only get through one problem. I think it's more valuable for you guys to see more problems and to get a feel for patterns and trends with this stuff. So with that being said, let's get down to brass tacks here. Okay, and Nick, did you pin it?
Y'all know how to pin stuff. It's not switching.
I think if you right click the window, you should get an option to pin.
I just pinned it.
Okay, cool. All right. So what we're doing for the next 3 lectures is I'm throwing up problems and we're working them out, right? We're not in a particular section. We're just using all the tools that we have in our toolkit to get through these problems. So it's going to be all over the map, but we're integrating all of this into one body of skills. So first problem from our marathon. We're looking at the series from n equals 3 to infinity of 1 over 2n minus 3 2n minus 1. Okay. I got a little bit of glare. It's like a crazy game of whack-a-mole with the glare, but it's not so bad. Right, so let's just start thinking about how to think, because often that's the hardest part, is where do we even start thinking? As we talked about yesterday, when we're looking at problems, our sort of first stop is to evaluate absolute convergence. If absolute convergence fails, then maybe it's conditionally convergent. And really, before any of that, your very, very first stop when looking at any series is to ask yourself, does the corresponding sequence go to 0? Right? So we have that very important theorem. We always want to have that in, at our fingertips, because that's the quickest way to eliminate a problem. If the sequence doesn't go to 0, then the series definitely doesn't converge and we're done, right? So sometimes it's easy to see, sometimes it takes a little bit of massaging to figure out what's going on with the sequence. Here, we ignore the series, that's the sequence, and that guy definitely goes to 0, right? We've got an n squared, basically a squared polynomial of n in the bottom, something fixed in the top, it's going to 0 all day. So that takes that, that eliminates that option. Now we have to start thinking a little bit more about how to approach it. So does anyone have any instincts about this? You see this and you think maybe it looks like something you've seen before. Where do we want to go with it?
I know we should check for absolute convergence, but honestly, I'm very tempted to do an integral test and then using partial fraction decomposition.
Okay, yeah, I think that you've got good instincts. Daniel has good instincts. So Daniel, why would you think that? What's compelling you to think that?
The n equals 3 is weird, and setting that as a limit for an integral to me makes things easier. And the bottom is fully factored,
Mhm.
and it just looks like a partial fraction decomposition problem.
Right, good. Yeah, so I think I agree with you on at least one point, which is I'm looking at this thing, it's a rational polynomial, it's fully factored, and that looks a lot like a partial fractions problem, and I totally agree with you. Now, the one tweak to Daniel's thinking is, now that we're in the series section, when you see something that may be amenable to partial fractions, your thought shouldn't be integral test, it should be telescoping series. Often if we find the partial fraction decomposition for this, we'll end up with something that's telescoping. Okay, so that's the insight. Looks like it might be telescoping. The integral test is great and all, but it's a lot of work, right? So you're going to have to do partial fraction decomposition anyways to integrate that thing if you wanted to go that route. So you might as well start there and see maybe if you have something telescoping. Why would we prefer to do it directly versus use the integral test?
Less work.
Less work, that's always a good reason. There's another better reason, or at least additionally good reason. What did we learn about the result that we get from the integral test? How does it compare to the?
It's not exact.
It's not exact, right? So if we integrate this thing, we're adding more crap in, and that's going to change that sum. Remember, the integral is going to give us something. If it converges, great. It definitely tells us convergence, but it won't tell us the actual limit. And if we have something that's telescoping, then that's something where we can find the actual limit, which is way better, right? So that's another reason why we might want to go at it directly versus use the integral test. Another good reason that you might not want to use the integral test is partial fractions is a lot of you guys' weakest subject. Now, that being said, you're still gonna have to do partial fractions decomposition on this thing. And I want you guys to get better at that because it's just algebra, right? But you know, adding integration into everything is just going to give you another opportunity to mess up. So anyways, let's try to do partial fraction decomposition on this. So what do? We say this guy should be equal to a over 2n minus 3 plus b over 2n minus 1, right? These are both linear factors. Their multiplicity is 1. So it's as simple as writing down that expression. Clear out the denominator. Right? And then you have options. You can start choosing values of n that you can plug in to see if you can kill some of the terms, or you can do the equating of coefficients. You all already know that my preference is for the equating of coefficients because I can kind of do it with my eyes. So what am I going to see? I'm looking at the n terms. I'm going to have a 2a and a 2b. And those will be the coefficients of the n. And then I'll have a minus a and a minus 3b. And those will be the coefficients of the 0 term. So we look on the left-hand side, we see we just have a 1. So that tells us that the coefficients of the n term must be 0 because there are no n's over here. And additionally, it tells us that the coefficients of the constant term must equal 1. So we got a little system of equations in the coefficients. Immediately, the first one tells us that whoever a and b are, they must be opposite each other, equal but opposite. So we can take this, substitute it in over here. So let me give that a name. I'll call that star. So sub star into equation 2. Okay, and that one's 2, and that one's 1. And what do we get? We get b minus 3b equals 1. So that implies that b equals negative 1/2. And since a must be equal but opposite, that means a is positive 1/2. So this is, a lot of you struggle with this, and I really want you to get good at it, to get better at it, okay? So I'm going to tell you right the hell now, there's going to be something like this on a test or a quiz, and you need to master partial fractions because a lot of you bombed this on the exam, and I want you to be good at it. So I'm telling you now, study it. Damn it. All right, so now we've got our A and our B. I'm running out of room. You'll have the lecture video on YouTube, so I'm going to go ahead and erase if you haven't copied it already. I've got to clear some space here. But we know who A and we know who B is now. All right, so this tells us that our series that we were looking at up here is equivalent to this series, 1/2 over 2n minus 3 minus 1/2 over 2n minus 1. Right? That's your A, and that's your B. I put the minus sign out front, which is fine. Right, so now we're gonna go at this directly. We're not gonna pull out the integral test. We're just going to see, this looks like a telescoping series. one reason it looks like a telescoping series is there's a minus sign. If we ended up with a plus sign, then we'd be dead in the water, okay? So having a difference here is important. And we notice that the terms here they differ by some small amount, right? One's ahead of the other one to some extent, but as long as it's only finitely ahead, then they should eventually start canceling each other out. So we're going to start expanding it. And what we're going to write down the nth partial sum. So we start at 3. And one thing I am going to do just to make the math easier or more direct is I'm going to go ahead and bring that 2 down on each of them and multiply it through the denominators, okay? So I'm bringing the 2 down. I'm multiplying it through. Okay, so that's what's happening there. It's multiplying through by that 2. So now we can start writing down the partial sum. We plug in 3. Here we'll get 12 minus 6, that's 6. Here we'll get 12 minus 2, that's 10. Next term, we plug in 4. We get 16 minus 6, that's positive 1/10, looking promising. And then we'll get 16 minus 2, that's 1/14. Let's just do one more for good measure to make sure the pattern holds. We plug in 5, we'll get 20 minus 6, that's a positive 1/14. Very good. And then we'll get 20 minus 2, that's 1/18. So we can see that there's some cancellation going on as we'd expect. And if I write the term that ahead of the nth term, so the n minus 1 term, then the minus sign on this guy will be 1/4n minus 6, or let's see, no, it would be 2. And then we'll have a plus. No, I'm getting that wrong. Well, what's going to happen ultimately is that the leading term is going to cancel, right? So what happens when we look at the pattern, right? The second term cancels with the first term of the next piece. So the previous term here, yeah, it should be 4n minus 6, and then we'll have a 1/4n minus 6 over 1/4n minus 2. And that's the nth term. So I like to use the nth term because then the nth partial sum, because the final term here will always just be what you see in the series, right? And so we see that everything cancels out in between except the first term and the last term, right? That's what makes it telescoping. And so now we know what the nth partial sum is, so we can take the limit as n goes to infinity. And we can see that this term right here is going to go to 0. So the limit will be 1/6. And so the beauty again is that the limit of the partial sum as n goes to infinity is precisely the value of the series. Those are equivalent. So we know that not only does this converge, but we know what it converges to. So we can rewrite it all the way back to the original form if we want. We know that all these things are equivalent. And you're done. So telescoping series are nice because you can get a hard and fast answer. So I like them. And there's some partial fraction stuff, which is cool, stuff you've seen before. So we're scaffolding, right? Skill building. Any questions about this?
Could you explain how you took the limit of 1/6 minus 1/4n minus 2?
So we're taking the limit as n goes to infinity, right?
Yeah.
Obviously 1/6 has no n's in it, so it stays put. This term has an n, a factor with an n in the denominator, right? It's a linear term with respect to n, and then it has a fixed value in the top. So the top stays fixed and the bottom continues to grow. And if we take the limit as n goes to infinity, then that bottom is going to go to infinity, which means we're going to get 1 over infinity, which is going to equal 0. So that's something that we're allowed to take for granted. When we have a 1 over infinity, that's not in an indeterminate form. We know what that equals. That equals 0. Does that help, or do you need a little bit more?
No, that helps, thank you.
Cool. All right. Let's keep rolling.
So we did partial fraction decomposition to make it look or fit into the general form of telescoping.
Correct.
That's the thought, okay.
That's the thought, yeah. So what you would have done with the integral test would have worked, and you would have converged, and you would have gotten a good answer. But had I in the problem said what does the series converge to, you wouldn't have had the right answer for that, right? So that's why it's important to take it on directly. We much prefer knowing exactly what the series converges to. All right, number 2. Not all of them are long problems. So take a second, look at this sucker, and give me your thoughts. Someone other than Daniel, he seems very eager to share. I'd like to hear either someone other than Daniel or Jackson. Love you guys, but I want other people to have space to talk. So who else has instincts about this?
Well, it has an n power, so it could be a geometric.
Could be a geometric, good.
It could be geometric.
Okay, if it's geometric, then what's the important thing to know? What determines convergence or divergence for a geometric series?
The R term, if it's less than 1, then it converges.
Good. So we need to figure out who R is, right? So how are we going to do that? Do we know who R is?
Well, not right now, but we
Not
can
right now. So what do we need to do?
because it's a negative power, we could do 1 divided by e to the n.
Good. Okay, so does anyone not see what E and C is there? Why those two things are equivalent? Does anyone need me to break that down? It's okay if you don't see it. Much better to know now and but not just take it for granted. Everyone sees it?
Yeah.
Okay, so these two things are equivalent. Remember, with geometric series, it's very important to make sure that you have agreement between the starting point of your series and the power. So remember, you could either have it starting at n-1 at n equals 1, and you'd have an n-1 here, or it starts at 0 and you have an n, right? So that's always important to check because we'd have to tweak it a little bit if that wasn't true. The next thing to check is the absolute value of our ratio less than or equal to less than 1 or greater than or equal to 1. E is 2 and some change. So 1 over 2 and some change is definitely going to be less than 1. So that implies you have a convergent geometric series. And when you have a convergent geometric series, you know precisely what it converges to. And that's going to equal 1 over 1 minus the ratio, which was 1 over E. And we can make that pretty by finding a common denominator and flipping it over, and we'll get the actual result. So that's a short and sweet problem, right? When you get these geometric series, it's quick to check that you have convergence and quick to write down the actual value of convergence. So as far as we know, the telescoping series and the geometric series are the ones whose limits we can actually assess directly. In some cases most cases we can figure out that it converges, but not what it converges to, right? So remember, in case you don't recall, that if we have a convergent geometric series, I'll write it like this. No, I'll write it even better. I'll write it like this. Then we know that that converges to A over 1 minus R, assuming R is less than 1, the absolute value.
If we know the exact value that a series converges to, does that imply that it absolutely converges, or does it not?
It's a good question. What do you think?
I don't know, that's what I'm asking.
I think that one has to be careful. It depends on the series. So, like a telescoping series could look like an alternating series, potentially. You could essentially you could write it down in such a way that it was alternating, maybe. And if you took the absolute value of that, you'd lose the minus sign and you'd lose convergence. So I don't have an immediate answer for you. My instinct is maybe. You got to be very careful trying to draw conclusions. I think the better bet is to do this on a case-by-case basis. Let me ponder on that. It feels right. It feels like a good instinct, but I feel like there may be a counterexample. So let me give it some thought and I'll get back to you.
Nice.
Yeah. All right. So now we're looking at the series ln to the ln of n cubed, n equals 1 to infinity. Just to follow up for a second, Daniel, I mean, something like this we know is absolutely convergent, right? I mean, this is an absolutely convergent series. I'm just saying your premise that if we know precisely what a series converges to, does that mean it's always absolutely convergent? That I'm not confident saying yes. Yeah. Okay. So, right, we're moving back to this guy, ln of n over n cubed. Let's hear some feedback. Someone other than Ian, Daniel, or Jackson. I know there's others in that room who are looking at this. So what are our feelings? What are our vibes here?
The one where we looked at the fact that ln of n is less than n to the c for any positive c.
Okay, good.
So ln of x is less than any power of x for a positive power.
Mm-hmm. So let's stop there. Keep that in your back pocket. Absolutely, if you see an ln, that's one of the things you want to reach for. But I want to back us up and say, what is, let's look at this in a very broad sense. Let's not just think about how we're going to solve it, but let's think about the structure here. Think about the numerator and denominator. Who's growing faster? What does that tell us? Maybe, what kind of energy may we get from that?
ln is growing slow and the denominator is growing fast.
Okay, that's good. So what does that gives us one thing immediately, which is what? Think about the sequence.
Converging.
So if we always want to think about the sequence, the corresponding sequence, what do we need that thing to do?
Yeah.
We need it to go to 0. And if we need it to go to 0, then we better, if we have a rational function, then we better have that denominator outgrowing the numerator, right? If the denominator grows faster, then that thing's going to diverge as a sequence. So we've got that, right? And who am I talking to? Is that Rogia that was talking to me?
Yeah.
Yeah, okay. So we got that. Now let's start building up our thought process. Now we know that the bottom is growing faster than the top. If the top wasn't there, Rogia, if say the top was just 1, then what would you be looking at?
Series,
Say it again.
E series,
P series, and would it be a convergent one or a divergent one?
convergent, because.
Why?
E is greater than 1.
Good.
Or is it 1 or 0?
It's greater than 1, right? We need it to be strictly greater than 1 to be convergent, right? If it equals 1, then you have a harmonic series, which we know is the classic divergent series. So if the ln of n isn't there, then we have something that looks like a p series that's convergent, right? Obviously, the ln of n being there means it's not quite a p series, right? But that's sort of our instinct, is that, hey, maybe it kind of looks like a p series. So, and even more so, or moreover, it looks like a convergent p series. So our intuition now is this is convergent, right? We're on the road to prove it's convergent. Everything that, all this talk, I think is really important for you guys to be able to look at these things and start thinking about the general features of the series / sequence. How do the pieces play together, and how might they work for or against each other in terms of convergence, right? We want to have a good instinct or intuition for this stuff. So our instinct or intuition is we have something that's convergent. Now, Rogia, now we pull out that observation, right? That very important fact, which is that we can make ln of n smaller than any power of n. So which one do we want to make it smaller than? We can choose anything. So what should we choose?
Does it really matter?
It does, yeah, because we're trying to build an argument that this is going to converge. So, there are choices that will not show that, and there are choices that will. So think about it like this, Regia. When I make a ratio of, if I say that the ln of n is going to be less than something, and then whatever that thing is, I divide it by n cubed, I want what results to be a convergent p series. So I could say it's less than n cubed, but then if I put it over n cubed, well, actually that works. So we could choose n cubed. Then since n is a positive number that's greater than 1, I can write this down. It's not going to change anything, which means that ln of n over n cubed is strictly less than 1, which means it's bounded above, right? So now what?
Wait, I'm a little bit confused. So do we just make the n power just something greater than n to the 3?
No, in fact, we don't want to do that. We don't want to make it greater than, right? Because if I said, hey, we can make it anything we want. If I made it n to the 4th, then you would end up with this is less than n, but n diverges. It goes to infinity, right? So, what we're doing right now is we're setting ourselves up for a direct comparison test. And we want, if our intuition is that this thing converges, then we want to set up in a relationship between its corresponding sequence and another sequence that traps it from above. You know, we want it to be less than something that's convergent. Remember, there's two ways that we can do this. If we thought this was divergent, then we want it to be greater than something that is divergent, so the divergent thing pushes it. If we think it's convergent, we want it to be less than something that we think is convergent. So if I chose into the fourth, then I'd be making it less than something that's divergent, which wouldn't help us. So we need to trap it above. So really any choice in n that's less than or equal to 3 will do it for us, for the most part. So we have to be careful, because if I'd made it 2, right? If I made it 2, then I'd say it's less than 1 over n. Actually, I was wrong about that, 3. So actually, this is good. See, I like to work this stuff out with you guys. So if we made it 2, right, we can make it anything we want. But if we made it 2, then we'd say it's less than 1 over n. And we know that the series 1 over n diverges. So that doesn't help us, right? We need to make it less than a convergent series. N squared doesn't work. We're making it less than a divergent series. N cubed doesn't work either, because then, yes, it's the sequence is bounded above by 1, but if I'm thinking about this as a series, then I'm summing 1 to infinity, and that's going to go to infinity as well. So yet again, I've made it less than something that's divergent. I need to make it less than something that's convergent. So there's an immediately good choice for n here, which is what? What power of n should we use? 1. Good. So if I make it less than n, then I'm making this less than 1 over n squared. And now I'm making it less than a series that is convergent. So this is convergent by the p-series test, right? So, we're making this comparison at the sequence level, but we're really concerned with the series. This is a tricky thing. It's easy to get mixed up on it. And in fact, I just did while we were talking. So you got to be careful. But I can say ln of n is less than n. And if I put the cubes back in there, then that means that ln of n over n cubed is less than 1 over n squared. And the series of 1 over n squared is convergent. That's what I need, right? Not that this thing is convergent, but that its corresponding series is convergent. So the series is convergent, and so that implies that this series is convergent. And that's by direct comparison test. So again, we could choose any power of n that we want, but there's a number of choices that were adequate, but the simplest one to choose is n to the first power, because then we get 1 over n squared, which we know is a convergent p-series. If we had chosen n to the 1/2, we still would have gotten a convergent p-series, right? n less than, we just need the resulting power of n to be greater than 1 in the denominator so that we get a convergent p-series. All right. Let's see, where are we at? 41. Okay. Cool. Next problem. We're looking at the series from n equals 1 to infinity of -1 to the n over square root of n. So I picked on Rogia. She stepped up to the plate. So let someone else start talking to me. What do we see here? What do we think here? Who's got ideas?
Looks like an alternating series.
It's an alternating series, okay. How about Kevin? What do you think? Is Kevin there?
Here.
You're here. What do you see? What do you think? How about you just say, do you think it's convergent, divergent, absolutely convergent, conditionally convergent? What do you think? Take a guess. Just throw something out there, Kevin. Go with your gut. What about Chris? Chris Haymaker, you there? See, Chris isn't there.
The
All
absolute
right.
convergent,
Say it again.
is it absolutely convergent?
Is it absolutely convergent? Well, let's look at it this way. Maybe the square root is making it hard to see, but remember, what is the square root as a power? It's 1/2. So ignore the -1 to the end. Just look at that thing. Imagine you were looking at, I mean, if we want to look at the absolute convergence, right, we're going to look at the convergence of this series, which is just going to get rid of the alternating component. And then what do we have?
Series is less than 1.
Well, it can be a series.
Well, it's a
It is divergent.
P is a 1/2, which is less than 1 such divergence.
Okay, so this thing diverges, right? And that's by P series test. So that tells us that this thing is not absolutely convergent. All right, so that means we have to then look at conditional convergence. Now, my hope with this problem was that this would be a quickie, because we talked about this just last class, right? We said when we were looking at alternating series, and we looked at the P series in particular, there was an immediate result after we did a bunch of analysis. We looked at these P series quite a bit, right? So when P is less than 1, and we'll go through the litany here, but when P is less than 1, then the alternating P series is conditionally convergent, and or when it's less than or equal to 1, and when P is strictly greater than 1, then the corresponding alternating P series is absolutely convergent, right? So that's one that you need to have in your back pocket. Y'all need to have that on lock. Alternating P series, you need to know the rule, because that problem you could write it down in one line, right? And not have to do all this analysis. But let's go through it. So we need, if we say Bn equals 1 over n to the 1/2 power, right? Then we need Bn to be strictly greater than 0. That's a check. We need it to be monotonic, non-increasing. So we need Bn plus 1 to be less than Bn, less than or equal to. And that follows fairly straightforward, since that this would mean that equivalently that n plus 1 to the 1/2 power needs to be where am I? Needs to be greater than n to the 1/2 power. And that's true, right? Since n is greater than, since this thing is greater than 1, n plus 1 and n are both greater than 1, then they're, you know, that if it's true for to the first power, it'll be true for any power. So we get that one. And then the last condition is one that we already know, which is that we need this bn to go to 0, and it's 1 over n to the 1/2 power, so that's a check, right? So that says that this series with the alternating component converges conditionally, right? And remember that this is a consequence of the combination of facts that it does not converge absolutely, but it does as an alternating series converge, right? So maybe it's important to say this explicitly. What all of this told us is that our series here converges by the alternating series test, which, taken together with the fact that it's not absolutely convergent, allows us to conclude this. So there's, you know, 3 things that we've figured out. We figured not absolutely convergent, but we figured out that the alternating series converges, therefore it's conditionally convergent, right? So we have to put that all together. You know, just getting the AST isn't sufficient, right? Unless you've already checked absolute convergence.
Oh, wait. It's because it's in the denominator. Okay, never mind.
Okay. All right, so we are pretty much out of time. We'll continue our marathon of problem sets tomorrow. I'll see you all in person. I look forward to working some problems out together. I'm glad that we have a chance to do that. And I'll post the video to YouTube as soon as I can. Y'all have a good one.
Thank you.
Thank you.
Yeah. Nick, you can go ahead and kill the recording and
So we should check for